Started. Shall go to the Tech Expo. Find a lot of good companies there to talk with. Everybody's got complaints. A lot of my students, they only want to talk to U.S. citizens. They all want to do defense. All they want to do is make bombs. If you wanted to make the targets, you should be a civil engineer. I mean, come on. Okay, so questions. Mitch? On the lab. I think I was anticipating a few of those. Anyway, so on the lab.
How, for those of us who don't really have a controls background, does it matter, or is there a guideline on figuring out how often you should update your controller output? Like, is letting it run every time the clock goes, is that too fast? Or?
Okay, so the question is, how often should you update your controller? The issue with how often you should update your controller, what you should realize is that how many timer ticks does it take to output one PWM wave? 32. So should you change it more often than that?
No.
Does it make sense to change the duty cycle of your wave while you still haven't output the last wave? Okay. How long does it take so there's also another aspect of this. So the first aspect is you should absolutely not change it more often than you output one wave, one complete period. The other aspect is, what's your time constant on your integrator? So when I've told people you need to integrate this and iron out your PWM signal to be DC, some people take that to the extreme, and they get 1 square mile fields on your capacitor. You get the hugest capacitor ever made, and you put it on the board, and you say, okay, I'm going to have the biggest capacitor ever, and it takes 20 minutes for you to actually integrate 1 square wave. Well, you've got to figure out how big is your time constant? How long does it take your signal to integrate? So if it takes longer than a period of your wave to integrate, it probably doesn't make sense for you to be updating your duty cycle more often than the settling time of your integrator. So 1 period of the wave or the settling time of your integrator circuit, whichever is greater. Now, I have put no stipulation on this lab about how long you should, or how quickly you should converge to the set point. If it takes you a while to get to the set point, so long as you converge to the set point, that's all I care about. Okay? As long as you get to the set point and you hold there. And if there is some minor oscillations around the set point, that's also tolerable. Now, you shouldn't have large oscillations, but you should at least settle down to the set point. Okay? Another question. Do the lab in the order that I told you. There's a reason why I told you to do it in that order. In particular, when you're doing the lab, you're going to get, and I've explained this one to a couple of people, you're going to get some curve that looks like frequency, and this is volts. This is for showing you what happens with VCF. Okay? So you're going to have some curve like this that if you apply a little bit of voltage, you get a frequency. You apply a big voltage, you get a big change in frequency. Where over here, this is the center. Or in other words, you're going to push the 1 kilohertz button and you apply no voltage, that'll be your frequency. So you're going to see a trend over here with a negative slope, where if you apply lots of volts, you get a big, massive change in your frequency. Okay? At some point, let's say it's right here, and I'm not really advocating this part of the line. Let's say that's 0. Okay? There comes a point when you apply enough voltage to your VCF that you completely squash the frequency that you're outputting. So this frequency goes to 0. Okay? You don't need to worry about applying more volts than that. Right? Once you've got your frequency at 0, you don't need to make it more 0. Okay? 0 is enough. 0 is 0 is 0. You don't need to make it even more 0 than 0. Okay. So, if you draw a vertical line from the point where you make it 0 over on your voltage line, okay, what you can say is if I apply a voltage greater than that, it doesn't do me any good. Now, let's extend this up, say, okay, that's my center frequency. How many volts does it take to range between no adjustment and the biggest adjustment you can make, which is zero out the frequency altogether? That's one thing you're going to have to discover. Okay. Is the range here, so you'll have some range between center frequency and 0. I've told you you need to handle small changes from your center frequency, not large changes from your center frequency. If your center frequency is a kilohertz, and you say, I want to handle small frequencies, you don't need to handle an error that changes you 800 hertz from your 1 kilohertz starting point. Okay? So in other words, you don't need to have a voltage range that ranges all over from 0 to the center frequency. You can take a portion of that. That's one issue. The other issue is when you're managing your controller, you need to make sure that you are able to adjust to make your system go faster and slower. Okay? How do you make it go faster and slower when this voltage frequency curve intersects the center frequency when I apply 0 volts? What that means is your starting point should be somewhere in here in the middle of the curve. This should be your starting point. Wait a minute. Are you telling me, am I telling you, that if you start here in the middle of your voltage range, or it could even be a subset of this, depending on where you pick how much of a swath you want to eat in your ability to change. Right here, if you apply a voltage to your VCF, if I'm saying this is your starting point, that means you're applying a positive voltage to your VCF. That means you're going to adjust even out the gate, even before you start, what the voltage that's being output from your function generator is. Yes, that's what I'm telling you. The starting point, where you assign a 50% duty cycle wave, should result in you having a positive voltage on the VCF. That will cause you to deviate from your initial starting frequency being a kilohertz. Well, okay, so how do you adjust for that? We want our initial starting point to be about a kilohertz. Okay? So you set this whole thing up, you output a 50% duty cycle wave, you send that to your VCF will adjust the output of your function generator so it's not a kilohertz anymore. You then adjust the knob of your function generator to make it be a kilohertz. And then you take your function generator output and hook it up to your board. Okay? The reason why is that allows you to start in the middle of your voltage range where you have the ability to have swing. So you can apply a more positive voltage to affect it in one way. You can apply a less positive voltage to affect it in another way. Okay? Okay. How many of all is this making at all remote sense to? There's a few of you that I've already gone through this. How many of y'all are like, what in the world is he talking about? Okay, those of you who are in that boat but aren't willing to admit it, this means you haven't worked on the lab enough. Okay? Where should you be before Monday? On this lab, you should be to the point before Monday. This is not before Tuesday. This is before Monday. You should be to the point to where you think you're done, but all you have to do is test it. Okay? You should have already done all the calibrations. You should have already written all the code. You should have implemented your interrupt service routine. You should have all the code integrated, and you should have started testing the whole thing, and you should be fairly comfortable with the setup. And then all you have to do is just start to tweak it and test it. because then your world will fall apart, and it will take you hours to debug the thing. Okay? Don't underestimate the time that it's going to take. That once you have everything quote-unquote done and all you have to do is test it, it will take some significant amount of time to work the kinks out of this system. Okay? So just realize that's where you should be with this lab. Mitch.
On interrupt service routine, is there a good way of knowing that you're doing too much work?
On an interrupt service routine, is there a way of knowing if you're doing too much work? Well, the way that you do that is, well, you'd have to run some code outside of your interrupt service routine and see how much work you're able to do with that code. You ain't seen nothing yet. Okay? This lab is not going to work the interrupt service routine too hard. And most of the time that main spends, it spends in a spin loop waiting for data to arrive from the serial port. And that's totally okay to mess that up on occasion. Because usually your interrupt, you have 2 full periods of the bit rate of the byte rate of your serial port. You'd have to have an interrupt last that long in order for you to miss a byte. So the amount of work that we're doing in this lab isn't a problem. The next lab, when we start doing, so 2 labs from now, when we start doing context switching, that gets to be a little bit more intense. But as we go, we'll be doing context switching and scheduling decisions and all kinds of other stuff, so that gets a little bit even more intense. So we've still got a lot more work that we can do without messing things up in the ISR.
Could you just compile it and somehow parse out what all the instructions are that are being run and figure out how many actual clock cycles it takes? Is that practical?
Okay, so the question is, how would you actually go about finding that out? If you wanted to quantify that, you could go about doing something like a profiling, and you're going to have to do some of that in this class, where you figure out how long it takes to run your interrupt service routine. You can use low-level, highly accurate timers. Usually the most accurate way is do the work that the ISR is going to do, but put it in a loop in main and disable all the interrupts and do it 1,000,000 times and figure out how long it takes to do it 1,000,000 times, and then divide by 1,000,000. Right.
What's a good way to find out what our proportional gain and integral gain are going to be?
What's the best way of finding out what your P gain and your I gain should be? You tweak.
So you make it so you can input it as it's going?
Well, the question is, do you make it so that you can input those as your program's running? Yeah. The user interface should already let you do that. You should start by not having a PI controller. You should start by having your I gain be 0 and just tweak until you get a P gain. And then when you implement an I gain, make your I gain small, like fractional. Yeah. Okay. Other questions? I've started grading the exams. I appreciate the work that some of you done, but really I don't need the extra help. So if you've left the problem blank, I appreciate that. But I don't need the extra help. Better if you just don't leave the problem blank. Okay? Next time, don't leave problems blank on exams.
Thanks for helping the curve.
Yeah, thanks for helping the curve. Okay, so you remember we talked about stacks and Stack Overflow last time? The one thing that I wanted you to take away from last time, you remember we have a calling convention. We push parameters onto the stack right to left, we push a return address, and we jump. The caller cleans up the stack when they're done. The callee pops the stuff off of the stack. You have to push you have to push registers onto the stack depending on whether you're whacking a callee save or a caller save register. All this stuff interacting with a stack, and you use the stack a whole bunch. Okay. Most modern architectures and compilers, they tweak the C calling convention a little bit. They don't actually use the C calling convention as I taught it to you. The reason why is because pushing and popping is expensive. So there are ways around the pushing and the popping. Part of Lab 5 is for you to figure out what the ARM architecture's C calling convention implementation is. So you're going to have to figure out what that is. Lab 5 involves you're going to draw a stack frame for an interrupt service routine. You're going to discover the C calling convention for the TS7200. How in the world are you going to do that? You're going to have to look at some ARM assembly. You're going to have to ask your cross compiler to output assembly code for you, and you'll have to look at what the assembly code's doing, correlate that with what the ISR stack frame looks like, and that will tell you what how parameters get passed. Okay? You're also going to examine how to use set jump and long jump for cooperative context switching. Set jump and long jump for fun stuff. So anyway, Lab 5 is nowhere near as tough as Lab 4. Okay? It's a 1-week lab, and it shouldn't take you anywhere near as much time as Lab 4 does. Okay? So Lab 5 is one of the easier labs of the semester. Lab 6, Lab 6 has got a gotcha in there that's kind of tough. Lab 7 is a little bit more intense. Lab 8 is really bad, and Lab 9 is the end. Okay, and it's really bad. Okay. But just so you know, we're at the hump here. This is the middle. We're crossing the threshold to halfway. Y'all want to quit while you're ahead? Okay. There might be some transients in the middle. Okay, so today we're going to talk about the deep mysticism that they don't tell you about in computer science. You know, this is one of the layers of the onion that you don't really get into until you start getting down into the nuts and bolts of how an operating system works. This is the fundamental concept. This is the core, the basis of this class, context switching. This is the fundamental how does concurrency work, okay? So we've been beating around the bush with it up to this point, but this is the guts, the meat of it all. And so we've really been building so that we can understand the stuff that I'm going to be talking about today, and we'll be applying this stuff the rest of the semester. But really, this is the basis of how do you do multitasking in a computer, okay? So if the stuff that hasn't excited you to date, if the stuff that we've done hasn't excited you to date, well, if this doesn't do it, you're in the wrong class, because this is it. I mean, this is great stuff. Okay. All right, so the book talks about concurrent programming. It defines it as the programming notations and techniques for expressing potential parallelism and solving the resulting synchronization and communication problems. Yada, yada, yada. Okay, what does that really mean? It divides it up into two things that concurrent programming subsumes. Okay? The first one is high-level programming mechanisms for implementing concurrencies on single-core processors. And number two, the means of specifying tasks in a high-level language. Okay. So the book's emphasis is on number two, how you use programming language constructs to specify tasks and concurrency. What we're dealing with in our class is the low-level mechanisms for implementing that concurrency. Okay? So we're not so concerned about, we are concerned, but the value in what I'm trying to teach you about embedded systems is in these low-level mechanisms for implementing concurrency. We also need to be aware of the high-level language mechanisms for modeling concurrency, because those facilities are important and will continue to be important as languages evolve and embedded systems actually adopt reasonable techniques for implementation. Okay. We've talked about concurrency. You've implemented concurrency. We've already done concurrency. Well, if you cock your head to one side and think about it for a little bit, yeah, we have done it, but we haven't done it really formally. So in Lab 3 and Lab 4, we've seen RPM run, we've seen PIT run, and we've seen a user interface run. Okay? So your user interface is polling the user saying, give me some data. At the same time, you got your timer tick, your PIT interrupt, your timer interrupt running, and you also have the external interrupt running. So whenever an external signal fires, this guy runs. Stops this guy runs. Whenever the timer tick expires, it stops the user interface, and then PIT runs. All these guys are running at the same time. They're kind of independent from each other, and they're triggered independent of each other, right? So in some sense, this is kind of like we have different tasks, different processes, or different threads all running, okay? How do we implement that? Well, we associate with, we have one main program that we're running, and with each of the other concurrent entities that we want to execute, we associate that with an interrupt service routine, and we specify some criteria for firing that interrupt. Okay. So in the main code, so this is extracted from main. We've got this little thing that says that outputs our square wave inside pwm.c. We wait for a time interrupt to occur, then we send DIO low, so that makes our square wave output a low, and then wait for a tick, then we send a high, then we send a low, then we send a high. So this is just outputting a tick inside main. Main runs effectively oblivious to when RPM executes and when PIT executes. It just says, I'm just going to wait until this happens. I'll just keep waiting. It isn't aware of when PIT occurs. It just reacts to whatever PIT does. Okay? But it's completely separate. Its implementation is oblivious to whenever it gets interrupted and whenever it executes. More important than just the separation of this and that main is oblivious is that the mechanics of how the concurrency is implemented means that whenever RPM executes, it doesn't mess main up. Okay? It's very easy when you're dealing with interrupts, if you don't do things right, that when your interrupt runs, it messes up your main code. And bugs like that are very touchy, very hard to figure out, very particular in how you approach debugging them. Okay, but nevertheless, we have the ability to have concurrency. You may ask the question, why do you need concurrency in embedded systems? The reason why we need concurrency is the embedded system talks straight to its environment. Your PC talks straight to you. But your embedded system has to talk straight to its environment. So what that means is that it might be applying the brakes in an anti-lock brake system, or it might be controlling an elevator. It might be, the missile guidance, any of the other applications for embedded systems that I've mentioned. All of them directly interact with our environment. Environments, the world, is analog and asynchronous. It doesn't react directly in the way that computers like to act, one step at a time. So when the environment says, I need attention, the embedded system has to react immediately to that. So as things occur, the embedded systems need to react to those things that occur. Otherwise, you don't interact with your environment correctly, and you don't apply your brakes correctly, and your car crashes. Okay, so in order to deal with things correctly in an embedded system, because it interfaces directly to its environment, we have to implement our embedded system as a set of tasks or concurrently executing operations. They have to be independent of each other, and they have to be able to interact with the environment at the times that are appropriate. Those tasks also need to be able to interact with each other. They need to be able to share data. They need to be able to synchronize and work cooperatively together. Not all tasks need to cooperate with every other task, but there are times where we have tasks that need to work together. Okay? All the tasks need to be able to run. What that means is that they are scheduled on the CPU. The CPU is able to execute instructions. So a task has to be able to access the CPU in order to do its work. All the tasks need to be able to access the CPU, and there has to be an entity which allows the task to access the CPU in the proper order, in the proper way, so that either some priority mechanism is satisfied or some fairness criteria is satisfied. Okay, task, process. What's the difference between a task and a process? Typically, nothing. Some people say process, some people say task, some people say that it's got a significance, but in this class, I just say process. Okay, what's a process? A program and execution. So what's a program? That's your executable. This is what you build from your source code. Okay, so you get to the program, when you execute it, it starts to run, then it becomes a process. So typically, what we say is, technically it's not correct to say your program runs. The process is what's running. The program is what you create. You create your process from your program. Okay, so a process is a program and execution. It has a single thread of control. What that means is that it does one thing at a time. It's a sequential program. It does one instruction and the next and the next and the next, produces those results, commits them to memory, and back and forth. Okay? Sequence of instructions controlled by a single program counter. The program counter tells you where you're at in your program. Okay? Processes can execute by sharing a processor. How do they share a processor? Well, some controlling entity allows one process to execute and then freezes it, and then allows another entity to execute and freezes that and switches back and forth. Okay? If you want to actually execute the processes in parallel, you have to have the ability to run two processes at the same time. That requires a multiprocessor or a multi-core machine. Okay? These are quite commonplace these days. But before we had multi-core machines, we had single-core machines that we had to deal with multitasking. Very frequently in embedded systems, we have just single-core, simple machines that we still have to deal with context switching. And even if you have a multi-core machine, you're going to have to deal with context switching, and it becomes more complex. Okay, if you have different processors, if you have multiple processors, you may have different approaches to how they can synchronize and share memory. So you could have this architecture here. It's called a shared memory architecture, where you have a processor P0 and a processor P1. They're on a bus and they connect to RAM, so both the processors access RAM, and they access the same RAM. So what that means is if P0 wants to share information with P1, it can put that information in the RAM and P1 can react with it, so forth. Okay? Shared memory architecture. Distributed memory architecture is like this, where you've got two processors, each with their own RAM. P0 does not have the ability to access P1's RAM. P1 does not have the ability to access P0's RAM. So how do they synchronize? This one has to package up a message and send it along the bus over to P0. Have we done this before? Distributed memory? Give me an example of where we did distributed memory synchronization in this class. A week ago on the test. Which part of the test? Problem 1 on the test is we have two computers, a host and a target. Each of them have their own memory. Your host can't access your target's memory. Your target can't access your host's memory. How did we have them communicate? We sent a message back and forth. What was our bus? Serial cable. Okay? So you're already doing multitasking, multiprocessing with multiple processors. Isn't this great? See, I teach you how to do everything in this class. And some say, I wish you wouldn't. Okay. The particulars of the synchronization and the data exchange approaches, they are very different for the two different types of multiprocessor architectures, but we're not going to delve into that. That's a topic for another class. We are going to deal with synchronization for a shared memory processor. Well, actually not for a shared memory processor, for a single processor, but the principles apply easily to shared memory processors. When you consider a process has a lifetime that goes through different states. We can model the lifetime of a processor as a state machine. Okay, so we can say that a process initially gets created. After it gets created, it gets initialized. After it gets initialized, it is quote-unquote ready. That means it wants the CPU, but it can't have it yet. Some other entity decides when that process gets to access the CPU. When it gets access to the CPU, it goes to the running state. When it's running, it runs for a while, and then that entity decides whether or not it gets to keep running, or it decides itself that it wants to stop running, and it'll either go back to the ready state, or it could go over here to the terminated state, where it's finished. Note, you don't typically go from the ready state to the terminated state, because under the assumption that we don't have somebody else that's going to kill the process, we just assume that a process will go to terminated when it's done. You can't finish unless you're accessing the CPU. So as soon as you're done accessing the CPU and you say, okay, I'm finished, you go over to terminated. There are lots of different variants of this diagram, and we will draw a couple of variants as we implement Lab 6 and Lab 7. Okay? And we're going to be implementing them and depending on them.
So, Justin,
yes?
with the wait or like sleep state, if you're waiting for something, would that be ready?
Okay, so if you have a wait or a sleep state, would that be in ready? It depends on how it's done. So if you have a sleep state, are you implementing it with a busy loop? If you're implementing it with a busy loop, you're still running. Or if you have a sleep state where you're actually yielding the CPU to another entity, you would probably go off to some other state that wouldn't be modeled in here that isn't ready, that is like blocked or waiting until some time happens, and then you'd have to depend on that operating system or that other scheduling entity to take the process that's waiting for a particular amount of time to make it back Just send it back to the ready state. Other questions? Okay. Okay. So let's suppose we've got a single core processor executing multiple processes. You must multiplex the execution of those processes on the CPU. One way you could do this, you could run process A, then run process B, then run process C, and back and forth, and you just execute this. So what this would be is it'd be something like you have a, we call this a cyclic executive, and we'll talk more about that when we get to chapter 13. But we have this process A that we invoke just like it's a subroutine. We'll call it a process, but we'll put all of its code into a subroutine. We have a main code that just has a forever loop, and we invoke A, then we invoke B, then we invoke C, and then we invoke A, then B, then C, and so forth, and repeat that. Would something like that work with Lab 4? Well, Lab 4, you've got the RPM interrupt and the PIT interrupt, and you've got the user interface. If you have an approach like this, you run A, then you run B, then you run C. You run PIT, then you run RPM, then you run main. Then you run PIT, then you run RPM, then you run main. Would that work? Hope you haven't done it like that. That would not work. Why wouldn't it work? How long does main take to run? All the time. It takes forever to run because you always have to be looking at the serial port. How do you say, go and check to see if there's data at the serial port, then stop checking to see if there's data at the serial port, and go back and check to see if it's time to run the timer? You want RPM to run whenever the external interrupt occurs. And you don't know when that's going to occur. So you can't plan it out like this, saying, I'm going to check to see if PIT's ready to run, and then I'm going to check to see if RPM's ready to run, unless this loop is ridiculously tight. And that just burns a whole lot of overhead in just doing the looping. So this isn't appropriate for Lab 4 because we have interrupts that need to happen based on external events. So, now the next question is, why in Lab 4 and Lab 3, when we're running two interrupts and main, how can the interrupts run without killing main? So if the interrupt service routines are written in C and they access registers, they access the state of the machine, how do we keep the interrupt from whacking the main program that's running that's also accessing the state of the machine? How did we work with RPM and PIT without having them kill main? We save the state of the machine first before we enter the interrupt service routine, and when we're done with the interrupt service routine, we restore the state. Okay? The state of a process is referred to as its context. Okay? So when we switch from one process to another, we're going to save the process of the process number 1. We'll load the context of process number 2. So you save context, you restore context. Later on, you could go back and you restore the context of 2 after you save the context of 1. Okay? So you can go, we just have to have this notion of what is the context of the process, and then we have to define how do we save it. So what is the state of a process? What is its context? State of a process refers to, okay, well, what's the process doing? What data is it operating on? And what has it done to this point? Okay, so what's the process doing? Well, that's referring to what instruction is it currently executing, or in other words, what instruction is it going to execute next? Because when an interrupt occurs, any instructions that are in flight, you let them finish, and then you remember where to go back to start again. So what is it doing? That's the program counter. What data is the process operating on? The data that's operating on is its registers. Okay? What's the history of its execution? We call that the call stack, and we also have the state of the local variables. So all the local variables of a process are all allocated to the stack. We talked about that last time. So local variables are allocated to the stack. Return addresses are pushed onto the stack. So if you have 20 function calls deep in a program that you're running, you've got to remember, I was at this location, this address of this instruction, in the context of this function, which was in the context of that function, and that function, and that function. You've got to remember the whole call chain, the whole call stack. Okay? So your program counter, all of your registers, and everything that's on the stack, it represents the state of a process. All right. So if we're going to save the state of a process, we need to save all that. Okay? How did we get away from having to do, did we do this when we were looking at an interrupt service routine? So we saved the registers and the program counter? Yes? No?
The register. Program counter.
Okay, the program counter is just one of the registers. So yeah, we saved the program counter and the register. Did we save the stack? So how did we keep the interrupt service routine from messing up the program stack? They have separate stacks, right? So remember that? You got two stack pointers. Your IRQ stack pointer points at a different memory location than your SVC stack pointer. So we have separate stacks. So we don't need to worry about messing up main stack because we have separate stack pointers. So if you have an interrupt that interrupts another interrupt, then you might be worrying about it messing up your interrupt stack. But by default, we don't allow that to occur. We say that you cannot handle another interrupt until the first interrupt is done. So you remember this code from IRQ interrupt ISR. All this was push this register, push this register, push this register. So we push R0 through R14, and then we do a branch to IRQ interrupt handler. So we push all the registers onto the stack. Why push all the registers? Because they're kind of like a little mini cache for variables that your main program's operating on. And we might overwrite the contents of those registers in our interrupt code, so we have to save what the main was doing by copying all the contents of all the registers onto the stack, and we'll restore them when we're done with handling the interrupt. Okay. Okay. Where did I interrupt the interrupted code at? So if you remember, we got to remember what was I doing when I got the interrupt. What was I doing is the address of an instruction. This is the instruction that got interrupted. Okay. Where do I store the address of that instruction? I store that in a link register, which is R14. But remember that we have two link registers. This is a shadow register. We have the SVC link register, and we have the IRQ link register. So SVC R14, or the link register for the SVC mode, it has the, so whenever the program in main is running, it's going to have a value in R14. It's going to have the value in its link register. It may or may not have saved it, but it's using that value. So R14 for SVC mode has that address. We use R14 IRQ. The hardware automatically takes the interrupted instruction's address and puts it into R14 IRQ. Okay? So the IRQ mode's link register has the address of the instruction we need to go back to. So this is an important register that we need to keep track of. Okay, so just remember, when we start, the bootloader puts us into SVC mode, which is called supervisor mode. Okay? We stay in, so that's why our main program runs in SVC mode. It runs in SVC mode because we never change it to a different mode. So our bootloader puts us into SVC mode. IRQ runs in IRQ mode. How do we get into IRQ mode? The hardware of the processor puts us into IRQ mode when we get an IRQ. What happens when that IRQ signal gets flagged? So if you remember, we have the VIC hardware. The VIC hardware detects an interrupt signal. The VIC hardware asserts the IRQ line to the ARM core. The ARM core stores the current PC into R14 IRQ. It changes the mode to IRQ mode. When it does that, it saves the CPSR register into SPSR IRQ. Current program status register. That's what CPSR stands for. This is where the modes of the processor are. This is where the condition codes are, and a bunch of other status information is in this 32-bit register. So if you want to toggle modes, you write to the CPSR register. So we take the CPSR, which has basically what we're really concerned about is the condition codes from the instructions that main was processing. We have to save those. That's part of the state of the processor. So we save main CPSR by copying it into SPSR IRQ. And then after we've copied that into SPSR IRQ, we write to the CPSR register, changing us into IRQ mode. Hardware does that. Okay? You don't have to have instructions that does that. So the ARM core stores PC into R14 IRQ. It moves CPSR into SPSR IRQ, and it changes our mode to IRQ mode. Okay. Next, the ARM core says, I have an IRQ. I'm going to go to the address of the only IRQ handler that we have in this system. And it assumes that the handler is at address 0x18. Okay? every IRQ gets routed to this address. It says, I'm going to execute the one single instruction that's at that address. Kind of interesting, huh? You might have multiple interrupts, but we only have one IRQ line, we only have one handler, and that one handler has to be at the address 0x18. So, that's interesting. What's at that address? Well, at that address is whatever we put there. You're already putting something there. You didn't know that, did you? So, inside some of the files that I've given you, I've got this code here. I've declared a global pointer, volatile unsigned int IRQ vect adder equals 0x18. IRQ ISR adder equals 0x38. So these are two global pointers. Okay, the first one points at address 18. Then I have this big comment explaining what's going on. Down here below, inside this initialize IRQ interrupt function, we set IRQ vect adder equal to this number, E59FF018. Okay? That's all you need to know. Got it? We can go on. What in the world is 0xE59FF018? We'll talk about that. That's what this whole business of this took a while to figure out what in the world that was, by the way. That was really painful. We had some example code that says, this is just what you got to do. But I had to go through and disassemble that and figure out what it meant in assembly. Okay. At the other address, which is 0x38 here, the second pointer, we say star IRQ ISR adder equals IRQ interrupt ISR. If you remember, this is the name of the routine. That's that assembly code that pushes all the registers, does a branch, and then pops all the registers. Okay. So then we have these other two guys, and we'll worry about those in a bit. All right. So E59FF018, that is a 4-byte instruction. It does the following. It says, move into PC the address that you find at 0x38. Let's see if I can say that better. What I'm going to do is I'm moving into PC the address that I find at 0x38. Okay? So what this says is 0x38 contains an address of a routine. I'm going to take that address, and I'm going to jump to it. So if I move an address into PC, that's the same thing as saying jump. So this is a fancy jump instruction. It says, instead of jumping to a label, I'm going to jump to an address that's contained in a memory location. The memory location that contains the address is 0x38. So I've got two addresses here. The address that contains the address and the address that I'm jumping to. So the address that I'm jumping to is not 38. It's the contents of memory location 38. The address that I'm jumping to is this IRQ interrupt ISR. Because at this location, I store the address of this instruction at address 38. So basically what I'm doing is I'm just jumping to IRQ interrupt ISR. Okay. So what happens on an interrupt is VIC detects the interrupt, it asserts the IRQ line. The ARM core reacts, it changes us to IRQ mode and saves the CPSR. It saves it puts the address of the interrupted instruction into IRQ's link register. Okay? Then what we do is we jump to the address contained in the memory location 0x38. How that works is we have that one instruction that says stored at 18 that says move whatever's at 38 into the program counter. That address is IRQ interrupt ISR. So effectively we jump to IRQ interrupt ISR. In IRQ interrupt ISR, we've already seen that. That's where we push all the registers and then we jump to IRQ interrupt handler. We've seen that one when I talked about interrupts before. That's the C code that I wrote that we can then access the VIC to see which interrupt source fired. What's the address of the handler associated with that guy? So we query whether this is VIC1 or VIC2. I pull out the address of the handler and I jump to the handler. So you save all the registers, you jump to IRQ interrupt handler, you look up from the VIC, where's the handler, you clear the interrupt, jump to the handler. Handler needs to clear the source. That's where that star timer 1 clear thing is in PIT that you guys have seen. Okay. Then you return. When you end up back in IRQ interrupt ISR, this pops all the registers, and then the final instruction does a return to the interrupted code by writing the LRIRQ to the PC. The instruction that we use to move the LRIRQ into the PC automatically moves the SPSRIRQ into CPSR. That automatically restores the mode back to SVC mode and lets us proceed back in main. And main is none the wiser. Okay. I wish I could say that you can just not have to pay attention to this mode switching business. This is going to be very detailed, very painful here in a couple of lectures when we talk about how this IRQ interrupt ISR's code is going to get very complicated in a big hurry, and it's all going to be about mode switching. So you got to try to grasp this mode switching stuff as much as possible now. Okay, so now that we've seen and we've gone over in detail every aspect of what happens on an interrupt, what part of that process is for saving state, and what part is for handling an interrupt? Is there stuff in there that involves saving state? Maybe we can learn from that and devise a way of saving the context of a process based on how interrupts are handled. So let's ask ourselves, where is the state of a program? The state of a program could be in heap, global variables, or stack. So this is where your variable is located. You can have a heap allocated variable, a local variable, or a stack, or a stack variable. Local variables are on the stack. Okay. As we access variables, those guys can be stored temporarily in registers. So registers hold the state of a process as well. So we all agree registers are important, but we need to know about where is the state of a process in memory. Okay. What we need to do is we need to make sure that if a process is running and we want to freeze it and run another process, that we freeze enough of it and we make sure that processes are separated enough so that when this one runs, it doesn't mess this one up. And when this one runs, it doesn't mess that one up. So obviously, if we don't save registers, we can inadvertently mess the other process up. So we have to avoid that by saving the registers. Anytime we can inadvertently share state that we don't mean to share, that's when we can mess up the other process. So we have to figure out where does sharing occur. So we have to ask ourselves, do processes share global variables? Well, it depends on what your system is doing. On our system, we are not having memory management. We're not having each process have their own memory, have its own memory space. So what that means is we're going to allow processes to share global variables. This is effectively the same thing as a thread. Okay? So we're not supporting virtual memory. We don't have a separate per process address space, so all processes share all the global variables. So we are going to say that, yes, processes share global variables. So what that means is we're going to allow processes to share global variables, and so we're not going to count that as part of the state of the process that you have to worry about saving. It's the individual process's responsibility to make sure it doesn't mess up somebody else's global variable. So we don't need to have the global variables be part of a process's context. Okay? Do processes share program counters? Okay, so each process is going to be executing a sequential program or a sequential set of instructions, and when you freeze one process, it remembers where it's at, and you go back to another process. That process is going to be, maybe it's in the same code, maybe it's in different code, but it's going to be at a different location in its process, in its program when it's running. Okay, so processes, you can't just, you share a program counter register, the program counter value is not shared between processes. So we can't share program counters. Do they share register values? We already talked about that they can't share register values. They each have their own different register values. Do processes share heap? Again, this depends on what your system is doing. If you have virtual memory and separate address spaces, then you have to worry about the heap and make sure that each process gets its own heap. Because we have shared address space, then we are not going to worry about the heap. We're going to say that all the processes share the heap. So we don't have to worry about making sure that the heap is part of the process's context. Now, if you have a local variable that you point to a particular location in the heap by calling malloc, that process could be part of the process's context. Or that variable could be part of the process's context. So you have to make sure that if you're allocating variables off the heap, that you remember where those variables are. Okay? So processes share heap allocated variables. That's a different ball game, and you have to keep track of pointers. Okay, that's probably a good stopping spot, and we'll continue this discussion next time. Okay, so make sure if you're stuck on Lab 4, you give me a call, you come to my office, send me email. I'd be happy to help. Make sure when you're testing SPRNF for reentrancy that you don't have your ISR and main both print to the same string. That does not test for reentrancy. If you want an explanation of that, come back and talk to me. Don't. See ya.